Okay. So here we go. Running a little behind in steel, but that's all right. Hoping to get through ponding here the next couple days. Hopefully, I'll give everyone a chance to review that before Monday. As of right now, I should be in class on Monday. Everything holding the way it's going, which is good. I'm pretty excited about getting out of my house. So with that, we talked about base plates. There's a homework out there. It's not due till the end of next week. There's also homework in advanced analysis, I guess for everyone except for Bryce. And then there's actually an advanced analysis exam next week. So don't forget about that as well. So when we think about ponding, I really think about kind of second order effects. So we've talked about P delta and P little delta effects, right? Where the initial displacement creates additional loading. Well, with respect to ponding, as it sounds, we're really going to be worried about, water that builds up on roofs. And not just water that builds up on roof due to rain loads, but on top of that, we have to worry about once the rain loads hit the roof, then it makes the roof deflect. Then it takes more rainwater to flow out through the drains and whatnot. And so we're really worried about that additional water on top of the rain loads. There's quite a bit of details here that I'm going to kind of glance over. The reason for it is, I'm going to try and start a timer here. The reason for it is rain loads are actually kind of detailed. Once you understand the rain intensity and the geometry of your structure, but there really is a requirement to understand the draining system for your roof. And so, really any roof system, the International Building Code requires there to be a primary and secondary draining system for every flat roof. And so, I'm not sure how many of you have been on a flat roof before, but if we go back here, this is a typical TPO, or they call it an EDM roof. Essentially, it's a rubber. All of the joints are sealed with basically like an asphalt or liquid kind of rubber cement, if you will. And then all these layers of rubber are, interconnected. And underneath this rubber, on top of our, metal deck or roofing structure, they lay down insulation. And that insulation is then laid down in such a way that it slopes to drains within the roof system. And so sometimes a roof can be free draining or edge draining. So that means, like for this roof we're seeing here on the right, that would mean that the overall roof slopes from one side to the other. And so it's going to run off the edge of the roof. Other times they don't have edge draining. Essentially what happens is we need to provide what's called a roof drain. I don't know why they have, this is not a scupper, but this is what a roof drain looks like. Oh, that shows both of them. Good. Let's see what this sends us to. All right, so that's a roof drain, right? And so there'll be primary and secondary roof drains, or in some cases, depending on the roof sloping and how the architect wanted things to move and look, sometimes the primary is what you see here, which would be a roof drain. Obviously, it's got a grill on it to keep large objects from going down in the drain and clogging them. This is a scupper. So I'm sure all of you have seen scuppers. They're usually in a commercial building. If you look at the sides of the walls, they're really like these little downspouts that just come out of the side of the wall. And so scuppers usually, they can be primary draining system, but they also a lot of times are secondary draining systems. So within the field of the roof, you would see these drains, and then on the edges of the roof, you might see these scuppers, or essentially knockouts in the side of the parapet that allows water to drain out the side of the roof. And you can kind of see the two there right here on the right-hand side. where it kind of pushes the water, allows the water to drain out of the side of the roof. And so, as I mentioned, we have rain loads and then we have ponding. And the building code requires us to look at ponding when we have certain conditions for a specific, what do they call it, roofing bay. Let's go back here. Look at this. It says susceptible bays. So ponding instability and ponding load. So we're looking at this right here. So this is 8.4 out of ASCE 7. They tell us that susceptible bays shall be investigated by structural analysis to ensure that they possess adequate stiffness to preclude progressive deflection, essentially instability, right? P delta effects, and adequate strength to resist the additional ponding load. So essentially, we as a designer, a structural engineer, have to determine, one, do we have susceptible bays? And two, if we do have susceptible bays, are they stiff enough to make sure that it doesn't have this excessive deflections, which then allow for us to carry more water before it drains off the roof, and then it ends up piling on itself. It's a P delta sort of effect. So if we start by looking at ponding, right, introduction of which, the definition here, as I kind of described, is really the accumulation of water caused by the deflection of the roof structure resulting in added load. Well, let's write this down. So the accumulation of water caused by the deflection of the roof structure resulting in added load, right? And that's the definition comes right out of ASCE 7. So as it relates to ASCE 7, right, they describe this susceptible base. So any of the following conditions shall be deemed to create susceptible base. And in the commentary of ASCE 7, they go and they have some illustrations of what these susceptible bays are. But as we look at this, so bays with a roof slope less than 1/4 inch per foot when the secondary members are perpendicular to the free draining edge. So this 1/4 inch per foot is kind of a big delineation that's made in the code. An interesting aspect of this is that the IBC does not allow you to have a roof slope less than 1/4 of an inch, except for in very specific circumstances. I think you can go down to 1/8. I would say that all the buildings that I've dealt with, essentially we might, as a designer, have to put a slope on our structure, right? And then on top of that, then they put insulation, as I mentioned, and then the membrane on top of that. And so if we sometimes, as a structural engineer, essentially dictate the slope of the roof based on the structure being sloped. And as I mentioned before, other times we're going to run a flat roof and then they're going to slope it with the insulation they provide between our structure and the membrane above. And so usually, especially if they do a structure slope, we're definitely going to be in that 1/4 inch or more per foot. And as I mentioned, the IBC requires some of that. So that's one susceptible base. Second is bays with a roof slope less than 1 inch per foot when the secondary members are parallel to the free draining edge. And so 1 inch per foot, free draining, you don't necessarily have a lot of those. Office buildings, typically I would say there's a lot of parapets in office buildings. I've only really, I guess one that comes to mind is like the Murdochs in Four Corners. And I think most of the Murdochs buildings that you see, they are all typically designed, they're all basically the same building. I've done a couple of them, and they free drain from the front of the building to the back of the building. So we sloped our structure. I think it was 1/4 inch per foot. And so the back edge is free draining. And so some of the bays at the back of the Murdochs, right, sometimes what we call our secondary members, we'll get to secondary and primary members, sometimes the secondary members, depending on the framing direction, are going to be perpendicular or parallel to that free edge. And so you have to be careful about that. So then 3, bays with roof slope of 1 inch per foot and a span to spacing ratio for the secondary members greater than 16 when the secondary members are parallel to the free draining edge, right? So again, something you need to consider as you look at the layout. Bays on which water accumulates in part or in whole or in part when the primary drain system is blocked, but the secondary drain system is functional. So that one's kind of open-ended, right? Bays on which water accumulates when the primary drain system is blocked, but the secondary drain system is functional. Well, usually, I've seen it a lot of times, architects, and you'd have to talk to a plumbing engineer, but a lot of times they have to, by code, provide a primary and secondary draining system. And a lot of times they'll just put them right next to each other and plumb them that way. Other times I have seen them use scuppers and then one of those drains I showed you. And so depending on which system's used, there may or may not be this possibility that if the primary is clogged, that there's going to require some amount of water on the roof before it actually gets to the scupper. One last thing they mention in here is the larger of the snow load or the rain load equal to the design condition for a blocked primary drain system shall be used in this analysis. So it kind of gets deeper, right? So obviously snow is frozen water. So if we think about snow load as it relates to a pounds per square foot value, right? A 30 pound per square foot snow load would be equivalent to almost half a foot, right? If we think about 62.4 pounds per cubic foot for water density, and if we have 30 pounds per square foot, that's essentially saying we almost have half a foot of water sitting on our roof. And I will tell you that is a lot of water. So what a lot of times what happens is 30 pounds per square foot, which is the state minimum in Montana, is enough water to where it's going to control over this ponding issue. And I think that's probably why the ponding is really something that doesn't necessarily get checked that often, even rain loads, for instance. So, I mean, for rain loads, if we looked at rain loads is in chapter 8 here, where this ponding instability and ponding loads come from. If we go and we look at the intensity of water, so if we go out to the city of Bozeman has, where is it at? City of Bozeman. So this is their design and construction standards, and this is their newest one that they're trying to adopt here shortly. This isn't the one that's currently adopted by the city, but every municipality, authority having jurisdiction should have some guidance to the designer. And this is where, as a structural engineer, we actually turn into somewhat of a civil engineer because we're going to go back to hydrology and think about what are those intensity, duration, and frequency curves relative to storms, right? So we have intensity, meaning inches per hour. We have duration, how long is that storm lasting for? And we have frequency, well, what is the return interval, right? So from 25 years up to, say, 100 years, or even less, 2 years. And depending on what we're designing, we're going to have different requirements. So if we go to, I wanted to show you this, storm drainage design, right? So this is in chapter 6. They talk about rainfall, and they say design storm depth and intensity at 6.6. So we're going to go to 6.6 here. Go to 6.6. Where are you? Here we are, 6.5, 6.6. All right. So they don't necessarily give us the curves in this new revision. The old ones they do. But in the new revision, they're just as specific as just saying, hey, this is Gallatin Field Airport, Bozeman Airport, and it's giving us, all these durations and the interval, and then this gives us a depth of water in inches, right? So in the rain design chapter in ASCE 7, they talk about the design requirement for the primary and the secondary drain. So primary is like, I don't know, a 60-year or 50-year return interval, I think like that, 60 minutes in 100 years or something. I can't remember, but that one's not the problem. The problem is the secondary. So if the primary is clogged, now all of a sudden we got to look at the secondary. Well, the secondary is going to have to carry a 15-minute duration storm that's coming once every 100 years. Well, you can see from this table here, at 15-minute duration at 100 years, you're at 0.9 inch depth, right? So from a 30 pounds per square foot value, we're looking at 6 inches of water on our roof, right? And so this being 1 inch, it kind of shows that we are going to add, we are designing for quite a bit more load on our structure. And there's actually an equation to take that that intensity, and then you look at essentially the static head that is required to drive that much water off the roof through your secondary drain. So I mean, it's definitely going on the outer edges of what we typically deal with as a structural engineer. But I was just trying to show you the relative magnitudes here. There's 1 inch of water is our storm intensity that we design for. But for snow loads in Montana, we're already putting 6 inches of water on our roof. And so we typically cover this ponding instability. I have done it a couple times on like larger structures. So, when you look at large structures, I think about Walmart. Right, Costco, right? Essentially buildings with large bays and low slopes, right? And so we'll get into checking it here. It's really easy, but so those are the buildings that we should be looking at. Also, if you look at section 7.11 in ASCE 7, they also say, for ponding, we need to look at, that's the snow load chapter, right? We say, hey, consider full snow load in our ponding, right? And why is this? Well, there's this time of the year, we call it spring, where the snow is melting, right? And so there's a time where we might have snow on the roof, but then it ends up raining, right? And so then the rain ends up saturating the snow. And so again, they want us to consider ultimately we're limited by the full snow load. But as we've seen here in Bozeman, the snow load is quite a bit more water than the design storm for our secondary draining system. And so that's probably why it doesn't get looked at all too often. One other reason is that ponding is not necessarily, we're not going to put the same amount of load on the entire structure, because as the structure deflects, right, we're going to make a dish out of the structure. And so the ponding is going to add additional load where we deflect the most, right? So depending on the roof slope and where our drains are located and kind of the valleys or the dishes, the low points in our roof, that's where the water is going to accumulate. And so even when we apply additional ponding loads on our structure, it really amounts to more of like a drift load that we see typically with snow loads. And so you're not putting that additional load on the whole structure. It also tapers. So even if, say, your design, rain event is 1 inch, and then the secondary drains are a couple inches above that primary drain, you're still only in the 3 to 4 inch range. You're really not going to be adding a lot more load or more load than what you would with snow loads. And so definitely ponding is an interesting one. But what you can do as a really quick check, and maybe a belt and suspenders, is for some of those larger structures, Walmart, Costco, Murdoch's, things like that, is that we can go through, especially with steel structures, and we can do some quick checks, quick calculations to just see how susceptible are our bays, your bays in design for that ponding instability, right? You can just confirm that we have the stiffness, adequate stiffness and strength that we can preclude ponding. We don't have to worry about it. And so ASCE 7, as I mentioned, has our two considerations in Chapter 8, which is for rain load, 7 for snow. This last piece here, I'll say, this is not done as much as probably should. All right, so Bozeman, 15-minute per 100 years storm event, approximately 1 inch. Well, 30 pounds per square foot is approximately 6 inches, right? So, there really is a hard comparison to make between rain and snow here in Bozeman. But it also depends on the orientation of your draining system on the roof. So, and like I said, I have, in some instances, just done a quick check review of the ponding aspects in AISC in some cases, just to double check. So if we look at AISC relative to ponding, we are referenced or sent to Appendix 2. So Appendix 2 provides guidance on ponding analysis. Okay. And this appendix says that the analysis methods that they provide are applicable to flat roofs with rectangular bays with evenly spaced beams and uniformly loaded girders, right? So this is your Costco, Walmart, right? Murdoch's, where we have a lot of times open web steel joists. So we have metal deck on open web steel joists that then frame to open web steel joist girders. And the frequency or the spacing of those joists is in such a way that it's small enough that the girders, you can essentially assume that they're being loaded uniformly, which happens a lot. So really, this appendix is really tailored for those big box stores type buildings, right? So if we look at a bay, and I've talked about primary and secondary here. If we look at a bay of framing, right? So this is a typical framing bay plan, right? So we have some wide flange columns. Those columns are supporting a primary framing, right? That primary framing is supporting a secondary framing system, right? And then on top of that secondary framing system is some sort of decking, right? It could be wood. I guess you could put wood on steel. I know Will really likes that. Or you can put steel on steel, which is even better, right? And we can use, I guess preformed light gauge galvanized metal decking, which is very common in steel construction. So the secondary framing is going to have some spacing S, right? And some length L sub S. That secondary framing is supported by the primary framing, that has a length of LP, right? So primary, secondary, spacing of our secondary, right? So that's our typical bay. And as the code reads up here, right, we need to look at each bay, right? So we might have 12, 16 of these bays that make up our building. And depending on the roof configuration within this bay, you may or may not have to worry about looking at this bay, right? So it's essentially we're looking at each one of these blocks, right? And we'll find that the analysis is going to be a little bit different if we're looking at an edge bay, where it doesn't have those joist framing or beams framing on the other side of girders. Maybe the girders are the edge of the building. And we can have some other unique scenarios where, for a Walmart or a Costco, we have these big masonry walls, bearing walls around the perimeter. And so at some point, the joist can be supported basically on a bearing wall, right? And so some other unique scenarios exist, and they give us some guidance as to how to consider those. So if we look at deflections for this system, we can start by looking at the girder deflection. Okay, so we look at the girder deflection. We're going to have a uniform load over a span of LP, right? And this girder is going to deflect, assuming a uniform load, some amount delta, and that displacement is assumed to be a half sine wave, right? And the reason why it ends up being a half sine wave, or at least why a half sine wave is close enough, is the fact that we made this initial assumption that our loading is uniform, right? And there's a bit more detail, and it's spelled out more in the commentary. So if you want to look at the theory or the basis of some of these methods, there's two methods, really a simplified and an improved, but with each of these methods, there's a derivation to essentially come up with these coefficients, depending on that relate to the stiffness of our system, right? Girders are the primary system versus the secondary system, and it all kind of is derived based on these assumed deflection states. So if we look at the girder deflection, we get what we see here, right? 0 at the supporting columns. We assume that those are definitely way stiffer than the supporting member. Then if we look at, scroll down here, the mid girder, secondary, deflection. All right, so now we're going to look at the mid girder. We're essentially looking at that right here, right? Those are the ends of our beam. All right, we just looked at the girder, so that's this guy here. And then now we're going to look at what's going on in the mid girder secondary deflection. So this is the secondary member, which means that we have a length of LS. It initially deflects a big delta, right, in the middle. That's this guy up here. Right? It initially deflects that big delta. So we're going to get that, and then we're going to call this little delta below. Right? Again, an assumed half sine wave deflection. Then finally, if we look at the end girder, or I guess end span, we'll call it end span, secondary deflection. It's looking more like our main girder deflection, right? Where we get a deflection of little delta at a span of LS, having a half sine wave assumed displacement. So what do they do here? Well, they came up with this idea that, in the center right here, that's going to be our maximum displacement, right? And so they came up with a way of, I guess it's using the displacement behavior, right? Assuming these half sine waves occur, and that, the center joist or beam is going to be the worst off because it's going to be deflecting already the girder plus its own displacement in the center versus what's going on out at the ends, right? So if we look at these joists or beams that are framing out at the ends, right? They don't have that initial girder displacement. They're just going to get the little delta. And so they ran through and came up with a way to come up with, or a couple different ways, to come up with determining if this system, secondary and primary, are stiff enough to where it limits those displacements to an acceptable level, okay? So if we look at AISC, Appendix 2, the first method they provide us, right, which is going to be, it's deemed as simplified, right? So they're simplified and improved. Because it's deemed simplified, obviously it's likely going to be the most conservative, right? And the simplest to implement. So if we look at, this is, I'll just say A2.1. And they give us two relationships. And they say CP plus 0.9 CS has to be less than or equal to 0.25. They also say that ID has to be greater than or equal to 25 times S to the fourth times 10 to the negative sixth. So what is this? It gives us these two coefficients, CP and CS. And if we look down here, CP is going to be 32 times LS times LP to the fourth, all over 10 times 10 to the seventh times IP. So if we look down here, based on our variables, LS is the length of the span of our secondary members, right, our beams, and LP is the length of our primary members, our girders, and then IP is going to be the moment of inertia of our primary members, right, so our girder members. So you can see here, this is really giving us a relationship for the span to stiffness ratio for our girders, with a little bit of influence of our secondary members as well, right? We have LS in there as well. And so what are they saying? Well, I guess before that, CS is very similar. It's 32 times not LP, it's S. Trying to give me my thing. S times LS to the fourth, all over 10 to the seventh times IS, right? So now this is a relationship of stiffness, span to stiffness, right? And now it takes into account what's the span of the deck to my primary members, right? Which can influence our ponding, right? If we have a long span between our beams, that's a higher potential for deflection and gives us higher potential for ponding, right? So looking at CP and CS, CP plus 0.9 CS has to be less than or equal to 0.25, right? So if that equation holds true, along with ID is the moment of inertia of the steel deck supported on secondary members, right? So a lot of times comes out to be a metal deck. If that moment of inertia of that deck is greater than or equal to 25 times S to the fourth, that's the spacing of the deck, right, or the span of the deck, times 10 to the negative sixth. If your deck is greater than that, right, and the first equality holds true, then you do not have to worry about ponding. You essentially have the adequate strength and stiffness, you can assume, and you can go about your business, right? So where do we get ID, right? All the other ones seem easy enough, right? We know the spacing of our beams, we know the lengths of our primary and secondary members, and we can get IP and IS, right? We can get IP and IS from the design tables or the dimensional tables in the steel manual, or a lot of times if they're open web steel joists or beams, you can go to the Steel Deck Institute or the Steel Joist Institute, and they have some formulas and some tabulated values for stiffness of some of those joists or girder designations. So ID comes from these tabled values, which I wanted to show you. So this is Volcraft. So this is the Volcraft. Whoops. Wish I could go. I want to zoom out, but I won't zoom out. Right. So Volcraft, steel roof and floor deck. I would say that Volcraft is definitely one of the predominant deck manufacturers in the industry, mainly because it is part of the Nucor family of businesses, which they essentially dominate the open web steel joist decking kind of world. Even pre-engineered metal buildings they do a lot of as well. And so they're just a big name. Excuse me. And so I've a lot of times used these Volcraft steel roof and floor deck tables. The reason why I do this is, as a designer, it doesn't necessarily matter which manufacturer you go for. They have standardized designations between manufacturers for the most part, right? There's definitely some one-off kind of designs that are out there for different steel decks that you might have to worry about. But for the most part, for what I've dealt with, any one of these different manufacturer tables will probably give you the same result. So you can see here for roof deck, there's a bunch of different profiles that they use. The most common one is 1.5 inch or potentially 3-inch deck, depending on what type of loads you have. The 1.5 inch metal deck is very common. You can see here it's made throughout all of their production facilities across the U.S. It comes in different gauges. So some of you have probably seen this on job sites before. Usually it's a galvanized product so that it doesn't rust. So if we go down here, so 1.5 inch steel deck, which is called 1.5B. I think it's back up here. 3-inch, here we are, right? So it looks something like this. You can get it in acoustical, so that's in this kind of ISO 3D view up in the top right-hand corner. You can see sometimes the deck's perforated at the bottom, and then they've got this insulation within the valleys. Norm has acoustical metal deck. It's very common in educational buildings, especially within areas that are in open areas, you know, places, hallways, stairs, things like that, where there's going to be a lot of noise. So they have this acoustical metal deck. So 1.5B deck, for those of you who've had masonry, I'm sure you're fairly familiar with all of this, but those that have not, essentially when you're doing metal deck specification or specifying metal deck, you get to really pull out design values out of a chart. So they give us number of spans, deck type, maximum construction span. So that makes sure that the deck is adequate to just install the decking and then have that construction load, right? So for roofs, it'd be 20 pounds per square foot. So they want to make sure that you can build it, right, without it collapsing. And so a lot of times we specify a minimum of 3 spans. As you can see, the values and the strengths go up as you go up in spans. So if we were conservative and we look at number of spans as 1, and say it spans 5 feet, which we'll see in the example here, and say each one of these deck types, B24 to B16, that's the gauge, which essentially specifies the thickness of the decking. So if we had an 18 gauge, which is a heavy metal deck, B deck, we have at 5 foot span, we can handle 168 pounds per square foot of total load, right? So that's essentially the maximum load that this deck can handle. And then the 152 is the amount of load that causes L over 240 or 1 inch of displacement, whichever is less, for this decking, right? So you can see that's a lot of weight for spanning 5 feet. It's only 1.5 inches thick. It can handle quite a bit of load. And so you just merely go out here and pick your deck, right? So a lot of times the standard decks that are specified in your structural drawings from whatever firm you work for, you usually don't have to mess with this too much. You might have to screw around with gauge a little bit up in the Big Sky or some of the higher snow load areas where there's big drift loads, where you get snow loads in upwards of 200 pounds per square foot. In that case, right, this deck wouldn't perform. It can't handle it at 5 foot. And so we've got to come up with some other way of dealing with it, right? Decreasing the spans, increasing the deck thickness. Maybe we do 3 inch instead of 1.5 inches. Okay, so that's our deck. We get that from the tables. So one other thing, this is a typical bay, right? Or we have kind of a secondary members attached or supported by primary members, which then are supported by columns. But sometimes that's not always the case, right? We're gonna have to use some engineering judgment here, or our own means of analysis, right, to come up with a solution for some cases. Like I think it's in this one right here, right? There may be a girder where this yellow column is. There may be a girder spanning right to left, which there probably is. But out there on the exterior wall, there isn't, right? And in some cases, if you have a thick enough metal deck, you might be able to span 10 or 12 feet. And so maybe you get rid of the girders in that drawing. And now all of a sudden the decking spans far enough. Well, I guess we get rid of the secondary members and the deck just spans between girders. And so that might be the case. And if that's the case, what AISC tells us we can do is we may consider deck as secondary member if attached directly to the primary framing. Right, so you have to do some critical thinking here and just try and understand the behavior of your specific bay, your specific condition. And we're going to keep it pretty simple for this class, but just to give a heads up that it's not always the standardized bay geometry like I'm showing here. I mean, a lot of times it is, don't get me wrong, but sometimes it isn't. Sometimes those joists or beams are supported by a bearing wall at the perimeter of the building and not a primary framing or a girder. And so it changes up the design a little bit. So that's as simple as it gets, right, for the simplified design. So if we meet those two equations there, we don't have to worry about ponding. We can assume that we have adequate strength and stiffness. We might fail that and want to sharpen the pencil a little bit, right? And we might want to use the improved design for ponding, which the improved design for ponding is A2.2, okay? One special thing about this whole ponding appendix is that it was all derived based on ASD, or service level loading, right? So ASD level loads. That is not a huge deal for the simplified because there really isn't any implications relative to loads. But it does come into play when we talk about improved design for ponding, because now we have to worry about the stress due to the impounded water, right? So F naught. So what they end up doing in the improved design is they give us these stress indexes. So they give us a stress index for the primary and secondary directions. Primary and secondary. Okay. So very simple equations, right? 0.8 Fy minus F naught over F naught, right? So what are they telling us? They're telling us that they limit the amount of stress that's allowed in the primary and secondary members to 80% of Fy. Right? And so then we're going to devise a UP or a US, and then we're ultimately going to take this value along with CP and CS to develop a limit to CP and CS, okay? Or limit to, let me just make sure there's a figure down here, put in there. Yeah, the upper limit of flexibility coefficient CP, right? So, F naught, right? So Fy is easy, A992, 50 KSI. F naught, stress due to impounded water due to either nominal rain or snow loads without ponding contribution and other loads acting concurrently. So what does that mean? Well, for our case, a lot of times I would just say, well, let's just throw the snow loads on there, right? And then make sure that those loads don't create a ponding issue. And so you either have to apply rain or snow loads, one or the other. Don't worry about the ponding contribution. That's that that triangular distribution loading that I was talking about. That has to do with, depends on where your drains are and your structure and everything like that. The other thing they're adding here, and other loads acting concurrently. So they want you to go through the ASD load combinations, okay? So relative to dead and snow, if we're gonna analyze that, it'd just be dead plus snow, right? We then get to use figures A-2.1 and A-2.2. And we go into those figures with either UP or US, right, or secondary, primary stress indices. Then the UP gives us, all right, we go from UP, we then utilize our CS, and then out pops at the end the upper limit of CP, right? US, utilizing CP, we get the upper limit of CS, right? And then we look at the CP and CS that we have, and we verify that we don't exceed this upper limit. And sometimes the upper limit, CP might exceed the upper limit might exceed the upper limit, but CS doesn't, right? What does that mean? Well, that means you need to go back and redesign the framing. And that means, and there's a number of factors that will play a role in what, ultimately the results are for the upper limits, right? Because it's a function of CS and UP, right? So if you increase the size of your primary framing, right, the girders, now all of a sudden if you increase the size of them, effectively reducing the stress, well then you're going to affect UP, which is going to then change what you end up with your upper limit. At the same time, CS plays a role in that one as well, right? Well, CS has to do with your secondary members, right, and the stiffness of your secondary members. So you can go about changing your girder and it's going to change the result, or you can change the secondary members, it's going to change your result, or you can change both, right? And so it's kind of up to you at that point to decide which way to go. As I mentioned, there are some special cases. If your secondary support is on a bearing wall, then you get to make the assumption that CP equals 0, right? Because your flexibility coefficient for the primary framing is 0, because that wall you're going to assume is infinitely stiff. If you have a slender deck supported on beams with column support, essentially saying that you have your beams are going to act as your secondary member, then you look at CS as it relates to the deck. So you would use the spacing for the deck, the span that is for the deck. You would use the moment of inertia of the deck, and so on, the length of the span. The span of the deck as well. So those are some of the special cases. I'm trying to think if I should just go all the way through. I'm not going to go all the way through. I'll do this example first thing tomorrow morning and get it out there, because I got to start looking at, already started looking at vibrations is our next thing. So I'll go through this, the last 4 pages here. Hopefully tomorrow I'll get that posted real quick in the morning, so you guys can get through hopefully all of these recorded lectures before class on Monday, which we should be starting vibrations. And then I'll get a homework out for ponding, and we'll just keep moving forward, try and get as much as I can. I know things have kind of slowed down here, which maybe you guys are excited about. I'm not too excited about it, but we'll see what we can make up here once I'm actually in the office. So anyway, stay tuned on